Hey everyone, today we're going to be talking about WiMAX, a wireless internet standard from the early 2000s, which was used to deliver broadband internet service using licensed radio frequencies such as 2.5 and 3.5 GHz, at a time where mobile data speeds were painfully slow. We'll be taking a look at the Cambium Network's PMP320 WiMAX platform, which came out in 2009 and was designed as a simplified, standalone system aimed at fixed wireless internet providers. I have a working setup here, but first, let's learn why all this was even needed.
Well, we're all on the internet now, but unless you're lucky enough to live in the right place or you live at work, you're probably creeping along with a 28.8 or 56K dial-up modem at home, waiting while web pages slowly fill your computer screen.
In the mid-2000s, the internet was exploding in popularity, and there was a huge demand for high-speed access to email, janky flash animations, and pirated music that might nuke the Windows install on your family computer.
That is not a small number!
Many internet providers were in the process of having DSL and cable service rolled out to customers in cities. However, in some towns and rural areas, high-speed internet was expensive and slow to deploy, leaving a good chunk of the population stuck on slow dial-up service. Even if you were in urban areas, there were still many cases where cable and DSL worked poorly. Around the same time, cell phones were also exploding in popularity. The contemporary 2G and 3G networks deployed in the mid-2000s were fine for calls and text messages, though the data speeds were very limited in capacity due to the small amount of radio channels allocated to that service. As a result of this low capacity, data plans were often limited to low usage and were expensive if you went over your limit. Later 3G network improvements increased speeds and carriers began offering marginally better plans, though the options for home internet from the cell carriers were still really poor unless you were just using the absolute basics. I recall both Rogers and Bell here in Canada offering plans in my area which had a few levels of data, usually stopping at 10 or 15 gigabytes. Then, you would be charged about $10 to $15 per gigabyte afterwards. That led to some really large bills when somebody in your house decided to download movies or video games. So clearly, there was some demand for a wireless service that could deliver fast home and business internet, which didn't have the limitations of cellular technology at the time. In 1999, the IEEE created a working group for wireless metropolitan networks dubbed Wireless Band, which created specifications for the 802.16 standard. The WiMAX name came out of the creation of the WiMAX Forum, which promoted interoperability between 802.16 equipment vendors and advocated for things like having government regulators allocate radio spectrum for this type of equipment. An early example of equipment using what appears to be a similar but not fully 802.16 standard would be the NextNet Expedience product line that was designed for primarily fixed services using outdoor, indoor, or vehicle-mounted client devices. I found one of these base stations sitting in a scrap heap covered in mud, and they're pretty large compared to a lot of fixed wireless gear operating in unlicensed frequencies, with most of it being the massive heatsink. The manual suggests that the maximum download capacity for one of these base stations is a whopping 3 megabits, and that it could somehow serve up to 250 users, which sounds more congested than a bee with a pollen allergy. Expedience was deployed by Clearwire in the US, and in Canada it was deployed as part of a Rogers and Bell partnership dubbed Inukshuk, which was probably named this way because any partnership between those two companies could be described as rocky.
Rogers was making me so mad, I switched to Bell.
I'm mad at Bell and I just switched to Rogers.
All Canadians are somewhere on the Bell Rogers anger continuum. Only Conglomerate makes sure you're matched up with someone in the same phase as you are.
This network sold services of up to 3 megabits download with caps of 10 to 30 gigabytes. Bell and Rogers shut down service around 2012, and I imagine the base station I have was part of this network. It seems that Expedience was also used by some cities for fast mobile access to the internet for public safety, which could be deployed to complement a two-way radio system. Later equipment that supported the full WiMAX standard was more capable and allowed for higher speeds as the standards evolved. Some cellular providers like Sprint used WiMAX in mobile devices like the HTC Evo 4G to increase the data speeds from around 2 megabits on their 3G network up to around 10 megabits using WiMAX. Around this time, Motorola, who had created the proprietary Canopy product line for delivering fixed wireless broadband using unlicensed frequencies, had released the PMP320 platform around 2009 to allow its customers to make use of the standardized WiMAX protocol in licensed spectrum, without all the complexities of the other WiMAX systems that was needed for mobile applications. That brings us back to this pile of stuff. I've managed to put together a test environment for this Cambium PMP320 system that uses all the major components that were sold for it. Some parts and documentation can have Motorola branding, since when the system was released in 2009, it was before their fixed wireless internet business was sold and spun off into Cambium Networks in late 2011. And it's still going Oh no. Ah, yikes. We can start at the subscriber module, which is an outdoor rated receiver with a built-in directional antenna. This was a white-labeled Gemtech made device based on the Sequans SQN1130 WiMAX chipset. It has a single 100 megabit Ethernet port that supports 48 volt power over Ethernet. So when it's installed, you would just run a single outdoor Cat5e cable from this receiver outside to a power injector inside the building, which could then be connected to a Wi-Fi router or PC. When installing it, you can use its built-in web interface to enter settings and check the signal. The maximum speed for this subscriber module is about 14 megabits download and 5 megabits upload, though the network is capable of much more. With that rated speed, I think I'm being a bit optimistic using a gigabit capable PoE injector. Since WiMAX is an actual standard, there are many different companies making compatible equipment. So we also have this later model Telrad CPE7000 that is also an outdoor rated PoE powered directional receiver that I'll talk more about later. Now, we're going to look at the equipment that you would find at a tower site that used the PMP320 platform. The most important thing here is the PMP320 access point, which can act mostly standalone. From what I gather, larger WiMAX systems needed a lot of different components to handle things like roaming and authentication. With PMP320, you can run a simple deployment with just the features built into this access point and basically any router. The access point is mounted to a sector antenna that could be used to cover a 90-degree azimuth, meaning you would need 4 of these to cover a full 360 degrees around the distribution site. The access point has a couple ports under a cover. There's an RJ45 Ethernet port with PoE to provide power and a network link to the access point, though it uses a pinout for PoE that was only ever used on the PMP320 and PMP430 models, which is a very Motorola thing to do, and it meant that I had to modify the pinout of a patch cable to power it up using a more normal PoE injector. The other port is an RJ12 jack used to connect an external GPS antenna for frame synchronization, which I'll explain in a minute. This port can also be used for factory resetting the device using a special RJ12 adapter, or a flathead screwdriver shoved into the port if you're an absolute menace. The AP is based on a Design Art DAN 2400 chipset, which was designed for inexpensive WiMAX base stations and even supported some sort of repeater mode that could use another WiMAX tower as its backhaul. Given that the web interface doesn't even look like any other Motorola wireless products, I imagine this is another Gemtech device that Motorola did some minor development on to make it fit into their ecosystem. The next device in line is the Cambium CMM4 or Cluster Management Module, which sounds a lot more exciting than it really is. This device will provide power on the Ethernet cable for the access points, and it will also give you a web interface that you can use to remotely reboot the access point if it's locked up. There's a bank of ports that provide the power, which is where you'd connect the access points. And then the data is passed through to the other bank of ports where you would connect a router or switch. So yeah, it's mostly just a fancy PoE injector. The PMP320 AP runs on 56 volts DC, which can be fed into the back of the CMM4, but there's also inputs for 29 volts, which you can toggle to in the web interface if you want to power other Cambium equipment that uses this PoE voltage. Having only DC power inputs is pretty common on this type of equipment, since a lot of telecom sites will exclusively run from DC power systems with large battery banks, which give them improved reliability and longer runtime in a power outage. The CMM4 also has an N connector on the back to attach a GPS antenna, which won't be for tracking a lost tower site. Instead, it provides GPS synchronization pulses through the PoE lines to all the connected APs by very briefly flickering the power. Access points in many fixed wireless deployments use something called time division duplexing, or TDD, which means that the access points will use the same radio frequency for both the upload and download direction by reserving certain blocks of time for both upload and download, kind of like how a regular pair of walkie-talkies only allows one person to talk at a time. To make efficient use of limited amounts of wireless spectrum, you can reuse the channels on access points, though this can be a problem if one access point is listening for a distant subscriber's upload traffic, while another AP on the tower a few feet away is transmitting at full power in the download direction. What GPS synchronization does is use the accurate 1 pulse per second signal from the GPS receiver to ensure that all access points in the network have a globally consistent metronome to sync up their download and upload cycles. This means that all the APs at all tower sites will cycle through transmitting, shutting up, and receiving at the same time. Next up, we have a MikroTik RB1100 AHX2, which is a network router that was released around the same time as the PMP320 stuff. It has a dual-core PowerPC CPU, 13GB Ethernet ports, and a pretty tired sounding fan. This will be handling the routing for our access point, and we'll dive into its configuration in a moment. Finally, we have this little guy, a B-Link mini PC with a quad-core Intel Celeron and 16GB of RAM running the Proxmox hypervisor that is acting as our server. In an actual deployment, this would be somewhere central like a data center instead of a tower site. On the server, I have a virtual machine running some software called Wireless ISP Toolbox that Cambium released in 2012. It's a front end to FreeRadius that you can access from a web browser and is used to authenticate subscriber modules onto the network, provision speed profiles, and keep track of when the equipment comes online. We'll circle back and talk more about Radius later. So let's sit down at the laptop and start looking at how this is all set up. First off, let's log into the access point. The original and default mode for this access point is to work in a layer 3 routed mode, which will have an IP subnet on the Ethernet port and another IP subnet that will be used on the wireless side for the subscriber units. On the settings page, we can see that the AP is set to external AAA, which doesn't mean that it's screaming externally, it just means that it'll use an external authentication, authorization, and accounting server, which would be FreeRadius running on our WISP Toolbox server. We also have the option of changing the sync source, which is where the AP will get its GPS synchronization pulses. Since I only have one AP, I just have it set to internal free run, which doesn't use GPS, but we can choose to get the pulses from the CMM4 connected to the Ethernet port, or a GPS connected directly to the AP's aux port. In WiMAX capabilities, we have our BSID, which is like an SSID in Wi-Fi terms. We also have the ability to fix the frequency that it uses, which is between 3.3 and 3.8 GHz. This range is going to be licensed or light licensed in most places, so you can't really use this frequency band without potentially interfering with things like cellular, unless you have a license or there's an automatic licensing system like CBRS available in your country. I have it set to 3.68 GHz, which is within the license that my employer has for this area, so I know it's unoccupied and safe to transmit on. At the time of recording these demos, that license was set to expire in over a month, since that spectrum has all been auctioned off to cellular carriers, because iSet is a bunch of hosers that didn't want to harmonize with the CBRS system in the United States, which will cause a bunch of good expensive equipment to turn into e-waste. I've also gone and lowered the transmit power to the lowest it'll go, since I'm only transmitting across the basement. The last part of the RF configuration involves the channel width, which is set to the max of 10 MHz. For reference, that's half the size of the smallest regular Wi-Fi channel. The upload-download ratio is set to use 75% of the capacity for download and then 25% for upload. The extended range feature adjusts the TDD settings to account for the extra delay when you need to increase the standard 11-kilometer range up to 40 kilometers at the cost of some capacity. The service flow section is where you can build some traffic shaping profiles. This can be a bit of a rabbit hole, but it can allow for some fine tuning for providers delivering services like telephone, who want to ensure that the network can give those sensitive services priority, or potentially give business customers priority on the network over residential customers. Since the network capacity on these APs is around 40 megabits if everyone has a great signal, and less capacity if they have a weak one, congestion can definitely be a problem when there's a lot of users connected, and fine tuning these these settings can help give everyone a somewhat usable experience. The entries can be set up in WiMAX Toolbox and then pushed out so you don't have to enter them manually. More on that later. Next up, we have our DHCP server, which runs on the wireless side of the access point to automatically provide IP addresses to the subscribers. On the next page, we can configure the range of addresses to hand out to the clients, or on the next page, we can assign a specific IP to a subscriber. Some of the last part of the configuration is on the networking page, where we can set up our default gateway IP, time server, and the syslog server to store any error logs remotely. The only other configuration left is our external AAA server settings, which we can point to the free Radius server running on the WiMAX Toolbox. In the internal AAA mode, you can assign service flows and authorize CPEs all within the AP itself for if you are just running a very small network, say for a campus or for security cameras. It's very clunky to do this though. Okay, let's take a look at the MikroTik router. There isn't a lot going on here in this simple test with the AP in routed mode, but we have a WAN port set up with a DHCP client and NAT enabled to share the IP it gets from my home network with the rest of the private IPs on the router. I have the 192.168.88 subnet set up for the server, the CMM4, and my laptop. I also have the 192.168.2 subnet set up for the PMP320 access point. If you're more networking savvy, you may know that we would need to set up some sort of route to tell this router where to find our 164.1 subnet on the AP's wireless interface, because the router doesn't have any knowledge of that IP range yet and won't be able to send traffic to our WiMAX subscribers. Well, the implementation guide suggests a few ways of doing this. The obvious way would be to static route, but there's a more automatic way to do this, using the magic of dynamic routing. Unfortunately, the AP uses the least magical dynamic routing protocol, RIP. I haven't used this crap since school over a decade ago, and it was basically obsolete then, along with a lot of other stuff I learned. If we throw RIP on the interface, the session comes up and we see our 164.1.0 network show up in our routing table and showing that it came from RIP. So now the router knows how to reach our WiMAX clients. We can now take a look at the WISP Toolbox server. On the tools page, we can see the logs aggregated from all the APs, and then the spectrum scan tool. Here, we can add a bunch of APs to a list and tell them to run a scan, which didn't work for me. But if it did, it would show a list of all the readings here. The important part of this software is the Radius section. Very quickly, Radius, short for Remote Authentication Dial-In User Service, is a protocol used extensively in internet service providers and corporate networks to be a centralized service that network devices like dial-up servers, Wi-Fi access points, and routers can reach out to and ask if a certain user or device should be allowed access onto the network, and what settings should be applied to this user. Radius is also used for logging things like how much data the user transferred and how long they were connected for. In the QoS profiles page, we can set up new service flows for different speed tiers or services, though we have to separately configure the upload and download parts. If you make any changes, you can go over to the clients page, which will list all the APs reaching out to the server, and you can then dump those service flows onto the AP. We can assemble these service flows into groups where we can tell it to apply the upload and download profiles together. I don't know what this CLS prof thing is, but I can tell you nothing works if you forget to add it. Finally, we can go over to the account section and get ready to add a new subscriber module by creating a username and password. Then all we have to do is pick a group for the speed profile that we want assigned to the subscriber. With that out of the way, let's work on the subscriber module. One quirk with these is that if you lose the IP address or password to access it, you'll have to factory reset it, but there's no reset button. Instead, you have to use a utility on Windows. This utility was kind of a pain in the ass because it only worked on Windows XP. So, when I was using these at work, I'd have to keep a full Windows XP virtual machine just for this 2 MB utility. 9 years ago, I managed to decompile the software, and despite not really knowing any C#, I managed to update the WinPCAP library embedded inside and recompile it, much to the dismay of people who were told by Cambium that it wasn't possible. Unfortunately, it doesn't seem to work on Windows 11 with the latest version of WinPCAP, but it sure beats using XP now. I just have to read the faded sticker on the side, then I can punch that into the utility to reset it. Now I can log into the SM, and we can start by adding our channel so the SM knows where to scan. Next, we'll go into the authentication menu and enter that account that we made in WISP Toolbox. Once we reboot the SM, we'll see it pick up the AP, get authenticated, and go into an operational state. It picks up an IP address from the DHCP server running on the AP, and the SM will act as a router with NAT to share this IP with a few connected devices, usually just a Wi-Fi router. If we run a speed test, we're getting the 5 megabits per second down and 1 megabit up. I can also go into WiMAX Toolbox again and change over to the wide open group. Kick the SM, and it will come back with the ability to pull around 13 megabits. Next, let's look at the Telrad CPE7000, which came out around 2013. This receiver is a lot faster than the PMP320 SM, reaching up to 40 megabits in some speed tests. Though the big draw wasn't that it was just a good WiMAX CP, it was also capable of being used with the newer LTE networks thanks to the Sequans SQN3140 modem card that could use both technologies. Telrad also sold access points that were compatible with both LTE and WiMAX, allowing operators of larger WiMAX networks to more gracefully transition their networks between the incompatible standards. One thing that I noticed with the Telrads is that they can be weirdly sensitive to the signal being too strong. It is not connecting right now. We go over, look at the laptop, and just keep hitting refresh. It goes into this synchronization state, then ranging, but it just never connects. But I'm just gonna move it. Put a foot away from the wall. Okay, and now we're operational. It's working. Back around 2015, the ISP I work for had a fairly large deployment of PMP320 and wanted to make the best out of the 365 spectrum that we had access to. We got in a bunch of these Telrad CPE7000s and a few of their LTE base stations. We would change out the PMP320 SMs on the customer homes with the new Telrads, connecting to the old Motorola APs in WiMAX mode. Then we could fire up the Telrad LTE base stations and have some customers working right. We ended up having a pretty bad time with the Telrad LTE system. If I recall, their support team was pretty overwhelmed, and both the software and documentation was pretty unfinished at the time. We eventually decommissioned the system in favor of other Cambium products, later making use of that 365 spectrum with the Cambium Medusa platform. The Telrad definitely has some similarities to the old PMP320 SM, like the same default login and the way the UI feels. That's because they were actually both made by Gemtech. Just like with the PMP320 SM, I had to make an account in WiMAX Toolbox and enter it into the authentication settings of the CPE7000. Compared to the Cambium SM, there's definitely more options for improved security and LTE features, but one major addition is the 2-line VoIP analog telephone adapter, allowing operators to deliver phone service without any extra components. Since fixed wireless is often used in lower density rural areas, there's a good likelihood that
cell reception isn't great or even available, and landlines can be expensive.
I set up a line in my Fusion PBX phone system for the Telrad, and it worked without too much hassle. Now that we have a couple subscriber modules connected, we can poke through the performance monitor options in the AP. The radio info page is a nice overview, so you could see the quality and strength of signal on your connected SMs. In the service flow stats, you can see the amount of traffic coming in at each modulation level per subscriber, so you can pick out the SMs with a weak signal level that may be dragging down performance on the AP. The frame utilization section lets you see how much of the upload and download capacity is being used. In order to use the Spectrum Analyzer feature, we have to change the operation mode to Spectrum Analyzer and reboot. While in this mode, SMs won't be able to connect, so you better make it quick before everyone starts calling in. You can lower the channel bandwidth for a more precise scan, but for this quick one I just left it at 10 MHz. As you can see, it's completely empty. In an actual deployment where the AP is on a tall tower, it's likely you'll see some spikes from APs on the same tower or APs on neighboring towers. You can use this info to see if you should adjust your frequencies, antenna down tilts, or output power. Now let's check out a feature that wasn't available in the original release of PMP320, Layer 2 Bridge Mode. This feature will let the PMP320 AP and SM transparently forward Ethernet, as if you had a long network cable stretching from the switch at the tower site all the way to the subscriber module. This made the PMP320 a lot more useful and easier to deploy for existing users of other fixed wireless products that work like this, where providers may have relied on bridging to assign IP addresses directly to customer routers using DHCP or PPPoE. It also allowed ISPs using the platform to offer private WAN services to transparently connect their customers' sites, or for enterprise users to extend their LAN across a larger area. First off, we're going to put the AP into Layer 2 mode. Save and reboot. When it comes up and our SMs reconnect, I can go over to the router where I already have a DHCP server running on the 192.168.2 network that the AP is connected to. In the DHCP leases, I can see that our Telrad and Cambium SM have received IP assignments directly from the router. I can confirm this if I log back into an SM and check its WAN IP address. Now, in an actual ISP deployment, you don't want your customers getting IP addresses in the same IP space as your network infrastructure. You want them all separated for security reasons. One way to do this is with VLANs, or Virtual Local Area Networks. VLANs allow you to carry multiple isolated networks across a single Ethernet link or within a single network switch. In this example, I created VLAN 10, which will have internet service for the customers delivered with DHCP. To use this, I'll go over to the subscriber module and enable bridge mode, enable the data VLAN, and then set it to VLAN 10. Now I can apply and reboot. Once it's all reconnected, my laptop will get an IP address assigned directly from the MikroTik router, instead of the subscriber module's built-in router. So that means we have transparent LAN connectivity the whole way through the PMP320 equipment. So that's the PMP320 platform. It was a bit of an oddball in the Motorola and Cambium product lineup and never really saw any further development. Cambium's replacement was the 3 GHz version of the Canopy PMP450 product, but while the speed and latency was far better, the ability for it to work through trees was not as good as WiMAX for some reason. The true successor to WiMAX, though, was LTE. As I mentioned with the Telrad stuff earlier, many WiMAX network operators shifted to LTE equipment to improve performance and take advantage of modern features like carrier aggregation, which allowed user equipment to bond multiple channels together for faster speeds. WiMAX operators that were also cell carriers were able to add the wireless spectrum used for WiMAX to the rest of the spectrum used for their cellular service, which improved mobile data speeds. Here in Canada, Rogers and Bell sat on their 2.3 and 3.5 GHz spectrum used for their Expedience fixed wireless network until eventually repurposing it for later 4G and 5G services sometime around 2021. Fixed wireless internet providers these days tend to use unlicensed frequencies like 5, 6, and 60 GHz for delivering fast home internet services. In some places like the US, some ISPs will use 3 GHz spectrum to deliver home internet using LTE, 5G, or proprietary things like Cambium's PMP450 platform or Tirana. Since the early 2000s, with cellular data service continuing to increase in usage as smartphones gain popularity, more spectrum has been allocated to cell carriers to meet this demand for faster speeds and more network capacity. Eventually, after LTE matured and 5G started rolling out, cellular network capacity finally got to the point where it is possible to offer usable home internet service through the cell network, especially in rural areas. Typically, providers will offer the service using either a portable modem that you can plug in and go, or for rural customers further away from a tower, they use an outdoor 5G receiver with directional antennas, much like the WiMAX devices we looked at today. The services, at least as offered by the carriers in my area, still have some limitations, but considering their previous predatory packages, they're a step in the right direction.